colligative properties that you need to be familiar with. The first one is called boiling point elevation. Keyword elevation. Whenever you add salt to water, the boiling point goes up. The boiling point of pure water is like 100 degrees Celsius. However, when you add salt to it, it can increase to like 101, maybe 102, depending on how much salt you add. But the boiling point goes up. The more salt you add, the higher the boiling point. It's going to continue to increase. So that's why it's called boiling point elevation. Now you might be wondering, okay, well, how does it make the boiling point of water or of the solution go up? So let's use sodium chloride as an example. So we have our sodium ions and our chloride ions. The presence of these solute particles, it makes the water molecules, it makes it more difficult for them to escape into the gas phase. And so for water to escape into the vapor phase, they need more energy. And so because you have to add more heat to it in order to get water to escape from the gas phase, the boiling point goes up. The temperature that's required to boil water increases. So the presence of the solute particles, they sort of block the water molecules from enter the gas phase, so it makes it harder. And that's why the boiling point increases, because you need more energy to basically, the water molecules need more energy to escape to the gas phase. Now the equation for boiling point elevation looks like this. It's delta T is equal to KB times M times I. Delta T is the temperature difference between the solution and the temperature of the pure solvent, in this case, pure water. KB is the boiling point elevation constant, and in the case of water, it's about 0.51 Celsius per molality. M, as you guessed it, is molality, and I is the Van Hoff factor. Now, molality is defined as the moles of solute divided by the kilograms of solvent. So that's how you find molality. Now keep in mind, in the saltwater solution, the salt is the solute. Water is the solvent. Combined, the saltwater solution is, well, the salt and water combined, it makes up the solution. Now, the next thing we need to talk about is the Van Hoff factor and how to calculate it. For a non-electrolyte like glucose C6H12O6, this is sugar. This doesn't dissociate into ions, so for non-electrolytes, the Van Hoff factor is 1. Now, for electrolytes like sodium chloride, this completely ionizes into 2 ions, so because you have the sodium ion and it breaks up into the chloride ion. So because there's 2 ions per formula unit, the Van Hoff factor for NaCl, that's going to be about 2. Now what about for like magnesium chloride or aluminum chloride? What's the Van Hoff factor for these? So for magnesium chloride, magnesium contains 1 Mg ion, and we have 2 chloride ions. So there's a total of 3 ions, so the Van Hoff factor is 3. In the case of aluminum chloride, aluminum has a +3 charge, and it's paired up with 3 chloride ions. So there's 4 ions per formula unit, so the Van Hoff factor is 4. And finally, what about, let's say, aluminum sulfate? How many ions are in this particular compound? So we can clearly see that there's 2 aluminum ions, 3 sulfate ions. So therefore the Van Hoff factor is 5, because there's 5 ions per formula unit. And so the more ions you have, the greater the boiling point of the solution will be. Now, the next type of colligative property that you need to know is freezing point depression. So if you think of the word depression, that means it's like down. Freezing point depression, this tells you that the freezing point of the solution decreases whenever you add salt to it. So if you think of in the wintertime, salt is usually added to icy roads. And what happens is the freezing point or the melting point of ice decreases when you add salt to it. And so it melts easier. And so it's harder for water to freeze when there's salt added to it. And so that's why that's why salt is added to ice during the winter. So it's harder to freeze. The roads don't get icy, and you can drive on them without sliding and getting into an accident. The equation for the freezing point depression is delta T is equal to negative Kf times m times I, where m is molality, I is the Van Hoff factor, just like the other equation. The only difference is the constant, Kf. Kf for water is about 1.86. As you can see, it's much higher. So if the boiling point of the solution goes up by like 1 degree Celsius, the freezing point will probably drop about maybe 3.7 degrees Celsius. So the change in the freezing point of water is greater than the change in the boiling point of water. As you can see, Kb is about 0.51, but Kf is more than 3 times greater. It's 1.86. So the freezing point of water changes much more rapidly than the boiling point of water. Now, the purpose of the negative sign is to show you that the freezing point will decrease. So if you have a pure water solution, it's going to freeze at 0 degrees Celsius. But if you have, let's say, a salt water solution, the freezing point might be significantly less. It could be like negative 8 degrees Celsius. So you can see the freezing point of the solution is lower than that of the pure solvent. And so that's another colligative property. The more salt you add, the lower the freezing point will be. So you can actually control the freezing point of the solution depending on how much salt you add to it. Now, the next colligative property that you need to know is vapor pressure. Vapor pressure and boiling point are inversely related. Whenever the boiling point of a solution goes up, the vapor pressure goes down. So when you add salt to water, because it's harder for the water molecules to escape the vapor or the gas phase, the vapor pressure of the solution is always less than that of the pure solvent. And if you wish to calculate the vapor pressure of the solution, it's equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. And so that's how you can find it. Now, in order to find a mole fraction of solvent, let's use the mole fraction of water. You need to get the moles of water and divide it by the total moles. That's the moles of water and the moles of the solute particles. By the way, let's say so let me write this as NH2O, NS for solute, the solute particles, and then N for H2O. Now there's something you need to be aware of this equation. Let's say if there's 1 mole of glucose, so the moles of solute particles will be 1. However, glucose is a non-electrolyte, and the Van Hoff factor is 1. But let's say if we have sodium chloride. If we have 1 mole of sodium chloride, keep in mind the Van Hoff factor is 2. So when you're calculating the mole fraction of water, you need to incorporate that 2 somehow. So the moles of solute particles is not 1 mole of sodium chloride. In fact, it's 2 moles of ions. So if you have 1 mole of NaCl, what you need to plug here is not 1, but it's a 2. If you're dealing with solute particles that are electrolytes, that can ionize in water. So make sure you're aware of that fact. And that's going to help you to get the right answer. Now, the last colligative property that you need to be aware of is the osmotic pressure. and its pi is equal to mRT times I, where m is the molarity, not the molality, but molarity. And molarity, which is a form of concentration, is equal to the moles of the solute particles divided by the liters of solution. I is the Van Hoff factor, T is the temperature but in Kelvin, and keep in mind the Kelvin temperature is the Celsius temperature plus 273. And then R is the gas constant, it's 0.08206. Now pay attention to the units of R. It's liters times ATM per mole times Kelvin. So if we put the units all together, here, let me rewrite the equation first. So molarity, we said it's moles per liter. R has units liters times ATM per mole times Kelvin, and the temperature is in Kelvin, and the Van Hoff factor is unitless. So as you can see, the units Kelvin cancel, the moles cancel, and finally the liters cancel, which means that the osmotic pressure is in ATM because we use the units 0.08206. So just make sure you're aware of that. And there's some times where they may give you the osmotic pressure, the boiling point of the solution, or the freezing point, or the vapor pressure, and you got to find, let's say, the molar mass of the solute. If you ever need to find the molar mass of the solute, here's what you need to do. The molar mass is the grams of the solute divided by the moles. Typically, they'll tell you how many grams of solute was dissolved because you can easily measure that. You can take the unknown sample, put it on a weighing balance or on a scale, and you can measure it. So typically you'll be given the grams. But in order to find a molar mass, the missing piece that you need is the moles. So if you're dealing with vapor pressure, you can find the moles by solving for the mole fraction. Once you get the mole fraction, find the moles of the solute particle. If you're dealing with boiling point elevation or freezing point depression, plug in the temperatures, solve for molality. And then once you have the molality, use the kilograms of the solvent to find the missing moles of solute, which you can plug in here. And then for osmotic pressure, you need to solve for molarity. Use that to calculate moles. And once you have moles, you plug it in here to get the molar mass. So that's how you can find molar mass if you're given the osmotic pressure or the boiling point of the solution. So that is it for this video, and thanks for watching, and have a great day.